Let's look at the consolidation due to radial flow, and I'll take this part in the next lecture. I have a large load, for example the Konkan Railway, National Highway, they want to build an embankment. I have a very thick clay deposit and it's going to take maybe 10-20 years. If you want to build a railway line or a highway, you cannot wait for 10-20 years for the settlement to occur. So what we try to do is install these vertical drains at regular interval so that I change the direction of flow. Water doesn't have to flow up or down, it needs to just flow horizontally. And by choosing appropriate spacing, I reduce the maximum length of drainage, the path water molecule has to do. Like here, maybe 1 to 1.5 meters or even less than a meter, so that the consolidation can be very, very high. So these are called vertical drains. Earlier we were using sand drains, now we are using plastic prefabricated vertical drains. So here is the embankment with some additional load. What you are saying is the water will flow into these drains and through the drains it will come out. So now the flow is through the drains, but into the drain it is all horizontal. Or if you look at the pattern, this is a square pattern. I have one drain here at equal spacing S. So you would agree that if I take the half plane or mid plane, this is a plane of symmetry. Water to the left of it flows into the drain here. Water to the right of it will flow to the drain here. From here, if I take it, it will flow up, down like this. So the zone of influence of each drain is a square, but square is very difficult to analyze. So we convert it into an equivalent circle. The radius is 0.546 into S, or if you find the diameter, it's equal to 1.13. Here, if I look at the triangular arrangement, look at the spacing between any two adjacent ones is S. So the zone of influence is a hexagon between these two like that. And if you convert that into an equivalent circle, it's equal to 0.525, so it becomes 1.05 times the spacing, and this is how we try to analyze. In case of square pattern, it's 1.05 times the spacing, and in case of triangular, 1.05. For square, it's 1.14. So you can see that hexagon is very close to a square. We also define a term N, which is a ratio of dE, the zone of influence, by the diameter of the well, dW. So N usually is 10, 15, 20, etc., depending on your design. And what you find is now the consolidation is radial, and towards the end it can be both radial and vertical. But let me tell you, if you have a thick deposit, the vertical flow is negligible. So you can see predominantly it will be into the well. And then we have the governing equation. First derivative of u with respect to time t is equal to coefficient of consolidation for horizontal flow, 1 by r, first derivative of u with respect to r, and second derivative of u with respect to r. And the solution now is a very simple one. 1 minus exponential 8 time factor with respect to horizontal flow by mu, and time factor is defined by CVT by dE square. And this term mu is nothing but n square by n square minus 1 into log natural n 3n square minus 1 by 4n square. Please remember, if n is more than 10, I can replace this, becomes close to 1, and this becomes 3 by 4, which is what I gave in the class. So this is very easy to remember, and this is how the consolidation takes place. And I want you to see here, once you take large n, the consolidation is very fast. You can get 90%, 95% before time factor of 0.4, 0.5. And this is how we try to calculate. And all you need to know is coefficient of consolidation in the radial direction, and the spacing gives me dE. Then you can combine vertical and radial flow. All that we do is add the vertical flow and the radial flow, and it's easy to extend whatever we got